Okay, so this P5 video is going to cover current, what it is, how to measure it, and also some things that can affect it. So what is current? Well, current is the flow of anything, but specifically electric current, right, exists when charges move, and the most common example of this is when electrons move in wires. And what happens there is we have the wire is made up of a series of these metal ions in a regular array called a lattice, and the electrons move through this lattice, and you can see the direction of electron flow indicated by this arrow. So what causes that to happen is that if we put a voltage across the wire, in other words, if we connect a battery or a cell to either end of the wire, then that will cause the electrons in the wire to flow in that way, and then we have a current in the wire. So we really must be clear that what's causing the current to flow is this voltage or potential difference across the wire. That's the cause, and the current is the effect. There's a slight unfortunate accident in history here, which was that when physicists discovered the idea of electrical current, they didn't really know about electrons. They knew that there was something flowing in the wire, and they needed to come up with an idea for what that was to do any problem solving, and they picked something and they said it was flowing the other way, which is unfortunate, and that's now called conventional current. It makes absolutely no difference to solving any problems, and that's the reason it hasn't been changed back, but it does cause confusion to generations of physics students. Suffice it to say that all you need to remember is that electrons are what's actually moving in the wire, but that for solving problems we use the conventional current, which flows the opposite way, and you don't need to think about the electron flow for your problem solving. This video is not going to cover any of the numerical problem solving with current. It's all talking about what current is. We'll talk about conventional current and how to use it later on. Okay, so that's the most common example of electric current for physics, which is current in the wire, in a metallic wire. But you can also have other examples. It's also important to note, by the way, as well, that unlike the static charging, there's not a charge imbalance in this wire. There are equal number of electrons and metal ions, or there's a balanced charge. So if the charge on the metal ion was +2, then there would be 2 electrons in the wire to balance that out for each metal ion. If the charge on the metal ion was +1, there would be 1 free electron in the metal wire to balance that out. So there's no overall charge on the wire. The only reason there's a current is because the electrons are flowing in that wire. Right, so another situation in which you can have electric current, it's useful to have another one to think about, and you should know this from chemistry because you cover electrolysis, is that if you have a solution which has ions in it, or a molten solid, so you've taken the solid, you've melted the ionic solid so that the ions can move about, and you put it into an electrolysis apparatus like this, then the positive ions, in this case I've just done sodium chloride, the positive sodium ions, which are orange, are going to be attracted to the negative electrode, and so they will move to the right in this case, and the negative chloride ions will be attracted to the positive electrode and will move to the left. And because then we've got ions which are charged, moving, then we have a current. Okay, so it doesn't just have to be electrons in a metal wire, it can be ions in a molten or dissolved ionic solid. Okay, so how do we measure current? Well, to get a number for current, we need something more than just saying it is the flow of charge. We need to say, define it in terms of how much charge in how much time. Now this is a bit tricky because you don't need to know what the unit of charge is for GCSE, which is the coulomb. I'm going to tell you about it now because otherwise it's kind of stupid to try and define what an amp is. In fact, the definition is kind of the opposite way round, but for GCSE purposes, we're going to say that we have 1 amp of current, right, if we have 1 coulomb flowing past every second. Okay, so if you imagine the little green dots in here are a coulomb, which is just a very large number of electrons. Okay, then what the ammeter in a circuit effectively does is it counts the number of these coulombs flowing past every second, and that gives us the number of amps. Now, obviously, it doesn't actually. There's not a little person sitting there counting, but that's effectively what it is doing. Okay, so if we let those coulombs flow past, then every time a coulomb flows through the ammeter, it counts. And so if there are 2 coulombs flowing through every second, then it's a current of 2 amps. If there are 5 coulombs flowing through every second, it's a current of 5 amps. That's what the ammeter does. It measures how much charge is flowing through it in per second in a certain amount of time. Okay, so how do we place an ammeter in the circuit in practice? Well, ammeters have to go in the flow of charge, and so they have to go in the existing wires in a circuit. In practice, if you're connecting one into a circuit, you set the circuit up without the ammeter, and then you will need to disconnect some of the wires, and you'll need an extra wire to connect the ammeter in. But it goes in the flow, so we're not changing any routes in the circuit at all. Okay, so this ammeter here is measuring the total current from the cell just underneath it. And it's really important to appreciate, very often people get confused about where ammeter placement means we're measuring the current for. So if you look at this, the current, as we'll see in a later video, can only change at a junction. Right? Basically, it splits when it gets to a junction if it's branching out, and it joins together and merges back again if the current comes from 2 branches into a single one. And because we're looking at conventional current, the conventional current comes out the positive terminal of the battery, which is the long side here, and flows through the ammeter. Now, that doesn't mean this ammeter is only telling us the current at one point in the circuit. Because of this fact that it can only change at the junctions, if you look at the highlighted red section here, if we put the ammeter here anywhere in this highlighted red section, it would give us the same reading, because the current can't change there. So this ammeter here is telling us what the current is in the cell, because the cell is highlighted red. It's telling us what the current is in this wire up here. It's telling us what the current is in this wire down at the bottom. That only stops being true when we get to the junction. So we don't know what the currents are in the rest, the white part of the circuit. We would have to use separate ammeters to look at those. Okay? So if we put an ammeter in this middle branch here, then again, between the 2 junctions, right, it would show us what the current was. So we could go either way from the ammeter, and we'd get the same current all the way in this part until we get to the junction. Same current in this resistor here. So again, this ammeter tells us what the current is in this resistor. And finally, obviously, the last placement does the same job. So it's important to realise that mistakes are often made when looking at circuit diagrams, that people don't fully appreciate what the ammeter is going to be telling you about the current in a particular component. Okay, so that's how the placement of the ammeter affects which current it's actually looking at. And the final thing is just to think about what can actually affect the current itself. Well, just a quick reminder then again that the ammeter is counting the total number of charges passing per second. So if I set this running, roughly speaking, and I'm sure somebody will probably sit there and count the charges and the time code on the video, but roughly speaking, that current there is about 1 amp, because there was 1 coulomb passing every second. Remember, the coulomb is this green blob here. So I'm just going to show you 2 different ways in which we could change that current to 2 amps, and I'll play it now. You can see this top version here, the coulombs are flowing much faster, and the bottom version here, there's just more of them. Okay, you very commonly hear people say that, oh, current is just how fast the charges are moving. Well, it's not quite that. How fast the charges are moving is one of the things that can affect it. So I'll just play it to you again, that last part. This second box down here, the charge is moving twice the speed as the top one, so that means we had a current of 1 amp at the top, we've got 2 amps at the bottom. In this bottom one, which is the last time now, the charges here are moving the same speed as in the top box here, but because there's just more of them passing, then again we get more current, because the ammeter is just counting the number of coulombs passing per second. So it is true to say that the speed the charges are moving at affects the current, but it's not the only thing that matters, right? How many charges are moving could also affect it. So in practice then, what things can we change in the circuit that will affect it? Well, given that the battery causes the current to flow in the first place, it makes sense that if we have a higher voltage on the battery or the cell, then that means we'll get faster moving electrons and so more current. And the last thing that can affect it is if we change the components in the circuit. And so that by components I mean things like bulbs and resistors. If we use different components, it will change the current in the whole circuit and in the branch where we change the components as well. And the reason for that is that the components will have different resistances, and we'll talk about what resistance is in a separate video.